So what if we have a content or a pre-measure on a given summary? Can we construct a content, respectively a pre-measure, on the ring generated by the given summary? So this will be what we do in the following theorem. So let's state the assumptions. So suppose I have a summary H on X, and the triple, the set X, the summary, and let's say new, be a content space. Then we claim that there exists a unique content space on or let's us restate that as a content mu from the ring generated by the summary such that the restriction of this content on H is new. In addition, if new is a pre-measure, then mu is not only a content, but it's also a pre-measure. Okay, so we need to prove several things. The existence of the content mu, the uniqueness, and later if mu is a pre-measure, we also need to establish that the content is also a pre-measure. So let us divide the proof in several steps. So the initial step, say it's step 0, would basically the construction or the definition of mu. Okay, we would like to define the candidate content as follows. So this is a function on the ring generated by the summary H. So we define this according to. Okay. First, let us recognize that what are the elements of the ring generated by H from a theorem that we have discussed previously. A is an element of rho of H if and only if A can be written as the union of a finite collection of elements in the ring H and it is pairwise disjoint. So the sequence is pairwise disjoint. Knowing this, we define UPB to be the sum of the contents with respect to nu of this partition. Okay. So that's the definition of nu. Now, let us verify that indeed the restriction of nu on H is basically the content nu. So taking an element H. Then if I set say n, if I take n to be 1 and A1 to be A, so that the union is it's the set A again, we have the following. Okay, so this is basically U of A, since A is in H, the restriction of the function and the function itself have the same values. And if n is equal to 1 and A1 is equal to A, the sum would reduce to U of A. Of course, this is valid provided that U is independent of the representation of A as a pairwise disjoint union of elements in the semi-ring. Okay, and what do we mean by that? If we could write A as another union of pairwise disjoint elements in the semi-ring, I should have the same value. Now, provided that this independence has been shown, then this implies that the restriction of H is new. This is the property that we would like to have, particular this one here. Okay. So this second step would be verifying this independence. So let's write that one. So the first step now is to verify this independence. Okay, now suppose I have another sequence, say B sub k, k from 1 to m. Okay, so we have a sequence of, or we have a set of elements in the semi-ring, pairwise disjoint, and I can also write A as the union of this collection of sets. Take note here, the number of sets m might be different from the number of sets n provided in this line here. Okay. It is possible that you could write the elements of the semi-ring by a different number of elements in the semi-ring. Okay. So from this, let's start with the definition of mu. This is the sum of the contents of A sub j with respect to nu. Now, we could write A sub j as A sub j intersection or A intersection A sub j. Why? Well, in this case, take note that A sub j is a subset of A. Therefore, the intersection would be the smaller set. And now applying the fact that A is the union of the B sub case, using the distributive property, this would be equal to the union K from 1 to M of A, or I should say B sub K, intersection A sub J. So here we use the fact that A is the union of the B sub case. Okay, recall that a semi-ring is closed under intersections. So this is in H because the A sub J's and the B sub K's are in H. First one. The second one is that the collection B sub K intersection A sub J, K from 1 up to M, and J from 1 to N. This is pairwise disjoint, okay, because the A sub J's and the B sub K's are pairwise disjoint as well. Now, we can apply the additivity of the content nu to write this as the sum from J equal to 1 up to N, and then the sum K from 1 up to M of nu B sub K intersection B sub J. Okay, so we have rewritten the sum of the contents of the A sub J's as a double sum of the contents of the B sub K intersection A sub J. Now you do the same process. So if you interchange the rows of A sub J and B sub K, in other words, what if I start with the content of the B sub case, K from 1 to M, then you do the same. So in the last equation, you interchange the roles of B sub K's and the A sub J's. So the summation would be reversed. Then A sub J and B sub K would be reversed as well. Okay. Take note that this sum here is equal to the second sum. Okay, here you use the fact that the sum is commutative and associative. Therefore, the order and the grouping with respect to the sum does not matter. Hence, these two double summations are the same. And with that, we can now conclude that the content of the A sub J's, J from 1 to N, is the same as the content of the B sub K's, K from 1 to M. And what does this equation tells us? Okay. This tells us that if I have another collection of subsets or collection of elements in the ring, here we denoted it by B sub K, and the union of this B sub K's is A, I can use this as well to the definition of the measure or the content mu here, and the result would be the same according to this last equation here. So in other words, the definition of mu does not depend on the representation of A as a pairwise disjoint union of elements in the semi-ring. And this indeed proves the independence that we have stated a while ago. Okay, so now we have the function mu. The restriction on H is nu, and it is independent with respect to the partition of A into elements of the semi-ring H. So the next step would be, of course, to verify that this is indeed a content. So that would be the second step. So here we show that mu is indeed a content. So the first one, let us look at the value of infinity with respect to mu. Take note that mu is the same as nu on H. Okay. Or if you like, this is the same as the restriction. So the function and the restriction is the same on the set where the function is restricted, and this is nu. And from the first property of a semi-ring, take note that the empty set is always in a semi-ring. Since nu is a content, this is 0. Okay. So let us add that there. The empty set is in H, and nu is a content. Okay, so that's the first part. Now, let us show that mu is additive. Okay, so for this, let us take two elements of the ring generated by H. Take note that this is the domain of mu. Okay, and this too is pairwise disjoint. Here we are verifying additivity with respect to two sets, but of course you could immediately extend this in the case of finite many sets. So for simplicity, we will only consider two pairwise disjoint elements of the ring generated by H. Okay. Now, according to the definition, if it is in rows of H, I can write this as, okay. For convenience, let us repeat what do we mean by A being an element of row of H. So A is the union of pairwise disjoint elements in H. And in a similar manner, we could write B as the pairwise disjoint union of elements in H, say B sub k, k from 1 to m. Again, the number of elements in general can be different as that with A. So let's correct this one. This should be a subset. Okay. Then we could write A union B. So this is simply combining or taking the union of the two representations. So just copy the representations and observe that this is a pairwise disjoint union of elements in H. Okay, so here we have represented the union of A and B as the union of pairwise disjoint elements in H, namely A sub j, j from 1 to n, and B sub k, k from 1 to n. And from this, according to the definition of mu, I can use this representation to obtain the value of mu. In particular, this is the sum j from 1 to n of mu a sub j plus the sum of mu b sub k, k from 1 to m. And you could easily notice now that the first term is mu of a, and the second term is mu of b. Okay. So this implies that mu is additive, meaning the mu of the union and the sets are, and if the sets are pairwise disjoint, then the mu of the union is equal to the sum of the values under mu. Hence, we have verified that indeed mu is a content. So that is now the existence. So from this theorem, we need to verify uniqueness. And that would be the third step. So step 3, uniqueness. So here we use a direct proof. So suppose I have another content, say gamma, such that the restriction of gamma on H is also equal to the original content nu. Okay. Now let us take an element of the semi-ring and suppose that this is partitioned as above. So in other words, it is the union of the a sub j's, j from 1 to n. Then let's start with the definition of mu. This is the definition of mu. Now take note that the a sub j's, being an element of H, is also an element of the semi-ring generated by H. Okay. And this implies that since gamma of H is equal to nu, and a sub j is in H, then here we could replace nu by gamma. Since nu and gamma coincide on the semi-ring H. Since a sub j is in H, so nu and gamma of a sub j are equal. Gamma being a content, it is additive, and recall a while ago that this is pairwise disjoint. So the sum of the gammas is the gamma of the union. Okay. However, as we have said, the union of the A sub j's is A. Since A is arbitrary, therefore, this implies that mu of A is the same as gamma of A for all A in the semi-ring generated by H. So two functions are equal. Recall that two functions are equal if and only if they have the same domain, codomain, which is the case for mu and gamma, and that the function values are equal for any element in the domain. In this case, take note that the domain of mu and the domain of gamma is rho of H. Hence, if you have another content whose restriction to H is new, then that would coincide with the content mu that we have constructed in the previous steps. Okay, so for the final step, so this is the fourth step, we would like to show that if mu is a pre-measure, then the mu that we constructed above is also a pre-measure. And for this step, we only need to show that mu is sigma additive, provided that mu is also sigma additive. Okay, so let's start with a countable sequence of elements in the ring generated by H, pairwise disjoint, having a union, say A, that is also an element of the ring. Again, we need to impose this because there's no guarantee that the ring is closed under countable unions. Okay, A being an element of rho of H, this means that I can write A as a union of pairwise disjoint elements of the semi-ring, and the number is finite. In other words, I can find B sub case, K from 1 to say M. These are elements of the semi-ring such pairwise disjoint such that A is the union of this B sub case. So the trick here is that we write the countable union as a finite union. And this is guaranteed because the property of the ring generated by the semi-ring H. Okay. In the same way, since the A sub n's are in rho of H, we could also say that for each index n, I can find a sequence, let's call them C and L, L from 1 up to M sub n. So here the number, the sets and the number of sets depend on the index n. A different index might need a different number of pairwise disjoint sets. And in this case, we could also write A sub n to be the union of this C sub n L. So here we now have a double index. So n here corresponds to the index of A, and then L here corresponds to the number or the index corresponding to the number of elements of the partition. Okay. Now, let us focus on a particular K from 1 to M. So look at B sub K. B sub K, you can write this as B sub K intersection A because B sub K is contained in A. Take note that the union of the B sub K's is A. Hence, a particular set in the union would be a subset of the union A. Then, A being the countable union of the A sub n's, I will replace that in this equation and then apply the distributive property. Hence, I have the following expression. So this is the countable union of B sub K intersection A sub n. The next step is to replace A sub n by this finite union. So now I could write the intersection as follows, applying the distributive property once again. This is B sub K intersection C and L. By a construction, you could easily see that B sub K intersection C and L, K from 1 to M, or I should say, take note that K is fixed here. So let's say N from 1 up to infinity, and L is from 1 to Mn. Or we could write it in this way. This is by construction elements of H, because B sub K is in H and C and L is in H. So this is H. This is also in H. Hence, the intersection is in H by, I think this is the second property of asymmetry. Okay. Moreover, you could also see that since the B sub K's, since the C and L's are pairwise disjoint and the A N's are pairwise disjoint, this is also pairwise disjoint. Okay. So in this case, take note that this is an element of H. Why? Because this expression here is the same as B sub K, and B sub K is in H, according to this assumption here. Hence, applying the additivity, or more precisely, sigma additivity of the content or the pre-measure nu, this implies that the content of B sub K is the sum n from 1 to infinity and the sum L from 1 to Mn of B sub K intersection CNL. Let us put this below. Okay, now if you look at the second equation here, B sub k intersection AN is an element of rho of H. Okay, so by the definition of the content mu, this is equal to, so the outer sum is the same, but the inner sum would be replaced to mu B sub k intersection AN. And we could do this because this is an element of the ring. B sub k is in the ring, A sub n is in the ring, therefore the intersection is also in the ring. Okay, so that would be the first equation. Now we apply this in the following equation. Thus, we would have the following. So mu of A, this is simply applying the definition of mu. Why is this the case? Since we have written A as the pairwise disjoint union of the A sub k's. Or I should say the B sub k's. Okay, now we plug in this previous equation. So we replace mu of B sub k by the one that we have obtained earlier, which is this series here. Okay, since the terms involved here are non-negative, it is permissible to interchange the order. Okay, and this should be M. And you could prove that because, for instance, if this is, if the series here is convergent, then it is absolutely convergent because the terms are non-negative. Hence, the order of taking the sum would be would not matter. If it is divergent, then both of the series would be divergent. Hence, we could interchange the order. And now, take note that if we take the union of the B sub k's, here we apply the additivity of mu because it is a content, and at the same time, take note the union of the B sub k's, k from 1 to m is equal to a. So applying these two to the previous equation, the inner sum is nothing but the content of a intersection A sub n. And here, noting that A is a subset of A sub n for all n, the intersection will be reduced to A sub n. Okay. And that is sigma additivity of mu. So it is a sigma additive content, hence a pre-measure. So again, mu is a sigma additive content, hence a pre-measure. And that ends the construction. So let us summarize the theorem with the following diagram. So you start with a semmering H, and you have a content mu on this semmering. Now we have here the ring generated by H, and we consider the following canonical map I sub H. And what is this canonical map? It is basically the identity mapping. So the canonical injection IH, H from rho of H would be defined as follows. So this is basically the identity map. However, the codomain is not the domain, only a subset of it. Well, this is indeed well defined because H is contained in the ring generated by H. So that's the canonical injection. So think of it as an identity map from a subset to the larger set. So we have constructed a content mu in such a way that this diagram commutes. In other words, if I go from IH and take the composition with mu, well, this is basically the restriction of mu on H. So given a content nu from H to the set of extended non-negative reals, I could construct another content now on the ring generated by the semmering in such a way that the composition of the canonical injection IH and the measure mu would be the same as the original pre-measure or another original content mu. Moreover, if mu is a pre-measure, then mu is also a pre-measure.